So we have two quizzes this week, and one is on Thursday, and that'll be over Dalton's Law of Partial Pressure and Avogadro's Principle, which we covered last week. And then we're doing Ideal Gas Law, and you'll have a quiz over that on Friday when it's just a half day. And then y'all will be out for spring break for a week. Anybody doing anything exciting? No? So on this journal, you have the total pressure, and it tells you that it's made up of neon and argon, and then you have the pressure of just the neon. So did anybody get the answer for the argon? And that's in the kilopascals? Okay, let's see if I remember. I don't remember because I did it yesterday. So that's probably that, except you would have needed to adjust it because it could have only been 2 sig figs. Because when you took your 239, right? And you subtracted your 184. So at that point, it gave you 0.55 atmospheres. So then whenever you change that from atmospheres to kilopascals, it just would have been 2 sig figs. So the 56 kilopascals. Okay. So that's all you need to do is just adjust that a little bit for the kilopascals for the sig figs. All righty. So if you'll pull out your notes, we're going to talk real quick about Dalton's Law of Partial Pressure, just kind of introduce this little process to y'all a little bit, and then move on really to Ideal Gas Law. If I can get my technology to work. So we're on applications of Dalton. Do we fill out all that? Yeah, we got that all filled out. Applications of Dalton's Law, and I'm going to go over that a little bit pretty quick because I won't cover that on a quiz or on a test. I just would like to kind of introduce it to you a little bit, if I can. I couldn't even get my overhead to work this morning. See if I have any better luck with that. Give up on that for a minute, see if I can do anything with this. Everything about this one is backwards. Wayola people. I feel like this always happens during this class. Let me right by your foot if you don't mind. I'll drop that little top of this. All right, thank you. Y'all give me just a minute. I'm gonna see if I can get this going because I don't even know. It's kind of hard for me to do the paper. At least if we're a little bit behind on this class, it won't matter because we can catch up over the next 2 days. Pause this for a minute. This apparatus is one way that gas can be collected, like after a chemical reaction, if they want to collect the gas for some reason. And the problem with it is that whenever that gas is collected, not only is the gas in there, but there's also some water vapor in that too. So that has to be taken into account. So if I wanted to find out what the amount of gas that was collected, I have to use a table to get my water pressure at that temperature. I'm always really proud of myself that I don't maybe accidentally say a little cuss word whenever I'm frustrated. Because sometimes I would like to take it and throw it.
You know what actually happened this weekend?
Yes, I would, Rodney. Make me laugh a little bit. I will enjoy that.
Me, my brother, and my little sister were all playing Super Smash Bros. Ultimate.
Okay, I have no idea what that is, but I'm assuming it's a game.
Yeah, it is. It's a fighting game.
Like Mario Brothers or no?
I guess they're not. I guess so, but not really.
Okay.
It has a whole bunch of different characters from different franchises, and just you can choose them and fight with them.
Okay.
Anyway, so we're playing. Both my dad's at work and my mom's out at the store, so we're home alone. We're playing, and after my sister Miranda loses a life, she accidentally curses.
Uh-oh.
Yeah. Yeah.
How old is she?
I can't remember.
Older.
Around 10 or 11.
Oh, so she's little, huh?
Yeah.
She's probably
yeah.
not allowed to cuss.
Yeah. No one in the house is.
Oh, okay. Not even your mom and dad?
Yeah. They do on occasion, but they tend to refrain from cussing. But yeah, the funniest part about it though is we're playing and then she just says it so casually.
And then just goes on about her way, huh?
Yeah, both me and Roger noticed. It was like, Miranda, did you seriously just say that? It's just it was so funny and so unexpected.
Yes, I try to refrain also, but every once in a while I might cuss. I did not grow up with my parents just never cussed. I mean, like if my mother said hell, that was, you knew you were in trouble. That was a big cuss word. We weren't even allowed to say shut up when we were growing up. So anyway, let's try this again. So if we collect this gas that we're interested in and we collect it over water, the problem is that we collect not only the gas, but we also end up getting some water vapor. So if I wanted to find out the amount of the gas that I had collected, I have to take out that water vapor first. So that's how it applies to Dalton's law of partial pressure. So if we come down here out of all these different formulas, the formula that we end up maybe using a little bit, and like I said, I'm not going to put this on a quiz or on a test, is that the partial pressure of the gas is going to be equal to the pressure of the atmosphere minus the pressure of the water vapor. And this pressure of the water vapor, you can get that from tables. So while I'm kind of making this into a small thing, there is an application in industry where this really does work. They don't have to go and figure the pressure of the water vapor every time. They can just pull out a table, and depending on what temperature it is, they can look up the pressure of the water vapor. And it also can be in different units too. This experimental method only works if the gas is insoluble in water, because if it's soluble in water, if it'll dissolve in the water, then it dissolves, and then you end up losing some of the gas that you're actually trying to collect. So this is an example of one of the possible problems that, how it would work with this. It says a gas is collected over water at 8 degrees Celsius in a 353 ml vessel. This temperature is not part of the problem. That temperature is only important so I can go to a table and look up the water vapor at 8 degrees Celsius. So the pressure of the water vapor at 8 degrees Celsius is equal to 8.1 torr. So that's a number that, you would have Googled or you would have looked up on a table. That's not something that you would be expected to calculate. So here it says we have a total pressure of 634 torr. So that pressure total is the pressure of the water plus the pressure of whatever gas we're actually interested in collecting. So it's like I'm collecting that gas, a byproduct of it is some water vapor. So kind of like the problem that we did today on the journal, if I'm given my total pressure, and then I was able to look up the pressure of water at 8 degrees Celsius, which is what I did, then I can set up in a little equation to find the partial pressure of the gas that I'm actually interested in. So I would say 634 minus 8.1, because that's what I'm doing to get rid of it. And I would end up with 626 torr is going to be the pressure of the gas. And then you'll see in a minute, we're using something called the ideal gas law. So if this was really being done in industry, they could then take that 626 torr and plug it into another formula and find out the amount of the gas that was actually produced, which is usually what they're interested in. Once again, just kind of showing you how that works in case you see it in future chemistry classes, and won't put that on the quiz. All right. So you can put these down if you want to. The first two are just basic Dalton partial pressures, bless you, like we did last week, where it's P total is equal to P1 plus P2 plus P3. This third one here is like what we did just now. So if you want to see if you can do it and get that answer, then there you go. But you won't see one like the third one on a quiz or a test. All right, so what I really wanted to spend my time on today is the ideal gas law. We'll be using this maybe up through after we get back from spring break. And it's a very handy law. It's a little bit different than your other laws because it only deals with one set of conditions. In other words, you're not having like the pressure started at 1 atmosphere and increased to 1.2 atmosphere. You're just talking about one set of conditions. And the formula is PV is equal to nRT. So P is my pressure, and that's going to affect R, and I'll talk more about that in a minute. Volume has to be in liters. If it's in milliliters, then you move your decimal back 3 places and turn it into liters before you put into this formula, because it's the only volume, is the only, in liters is the only thing that will cancel. Moles for my N, R is called the gas constant, and then T is your temperature still in Kelvin. So the ideal gas law is derived from Boyle's, Charles, and Avogadro's. So if you look at your R right here, there's a value of 0.0821 liters times atmospheres divided by moles times Kelvin. So that is one possible value for R. That is the R value that you would use if your pressure was in atmospheres. But if you look at your pink sheet, there are some other values. So let's look at our pink sheet real quick. So on the side that we have the pressure conversions, you'll see right below them we have R equals ideal gas constant. And you can see the only difference between each number, is what pressure unit you are in. So in other words, if your pressure is in ATMs, you would want to use 0.0821. If your pressure is in kilopascals, then you would use 8.31. If it was in millimeters of mercury or torr, because we know those are the same thing, you would use 62.4. So that's what I meant by your pressure will affect your R. Some people choose to convert the pressure always to atmospheres, and then they would always use this value because that's the most common one. I don't do that. I choose to just leave my pressure if it's given to me like it is and change my R. And you don't have to memorize these because you'll have your pink sheet. So the difference is just what the pressure units are. If you're trying to find pressure, if that's your unknown, then you would want to use your 0.0821 because it's the most common one. And that means that when you found your pressure, your units would be in atmospheres. So we'll be referring to that. If you look on the other side of the paper, then you can mark your ideal gas law. It's under behavior gases. It's right here. That's your ideal if you want to mark it. PV is equal to nRT. All right, let's go back at our notes. We really don't do any labs really during the gas laws because they're kind of hard to do in our lab setting. So it'll probably be when we get to our next unit, which is solutions. We have several labs that we do. All right. So in reality, an ideal gas does not actually exist. We talked about that right at the beginning of the notes. For our purposes, we assume there is an ideal gas or that real gases behave like ideal gases as we move through this unit. Real gases behave most like an ideal gas at high temperature and low pressure. We also said that at the beginning of our notes. And that's because the particles are farthest apart. Because an ideal gas does not really have much interaction between the particles. So when gas particles, temperature is real high and there's low pressure, they can spread out farther. And so that's when they're most going to approximate a ideal gas. So the ideal gas constant R has different values like we just talked about. And this is just a derivation of the formula. So that's how it was derived. I've never actually derived a formula by myself, so I'm going to assume that was a good derivation. So once again, when you were choosing your R, you can do one of two things. You can always change your pressure to atmospheres and choose your 0.0821. That's what it says right here. Or you can leave your pressure as it is and change your R, which is what I prefer to do. All right, let's look at a couple of examples here. And like I said, the difference also is going to be that with ideal gas law, we only have one set of conditions. There's not going to be a P1 and a P2 or a T1 and a T2. So our formula is PV is equal to nRT. So my first example says, what pressure will be exerted by 0.4 moles of gas in a 10-liter vessel at 27 degrees Celsius? So 27 plus 273 would give me my temperature of 300 K, because it always has to be in Kelvin. So I'm trying to find my P, that's my unknown. I have my N, liters is my volume, and I have my temperature. So I can fill everything in. So P is my unknown. My volume is 10 liters. My N is 0.400 moles. For my R, I'm going to choose my 0.0821 because that's the most common one. Out of the way. And the units of that on that are atmospheres times liter divided by mole times Kelvin. So there's my N, R, and then my temperature was, what did we say it was? 300? And there is my temperature. All right, so I need to solve for my P, so I'm going to divide each side by what? If I need my P by itself. 10 liters. 10 liters is all of this. So all of that's what goes in your calculator. 0.4 times 0.0821 times 300 divided by 10. And I think it was 3 sig figs. So I got 0.985. We were trying to find pressure. So all these other things, liters canceled, moles canceled, Kelvin canceled, and the only thing I had left was atmospheres, which makes sense because I was trying to find pressure. So my unit is atmospheres. Anybody have any questions on that one? Or do they get any different numbers? Remember, since this was my unknown pressure, I chose to use 0.0821, so that would give me my units of atmospheres. All right, let's look at another one here, and then y'all can give some a try. All right. The next one says a sample of methane gas contains 1,500 liters at a pressure of 15 atmospheres, a temperature of 45 degrees Celsius. So if I had 273 to that, I would get 318 K. How many grams of methane are in the sample? So can I use ideal gas law and figure out how many grams of something are in there? PV equals nRT. Which one of those could be related to how many grams? N, exactly. If I can figure out how many moles of methane I have, then I can use the molar mass of methane to get to grams. And that's the relationship that you'll see a lot of times. Either figuring out moles and converting to grams, or having grams and converting to moles. So that's what we're going to do. So my N is my unknown. This is my pressure. 1500 is my volume. There's my temperature. Since my units are in atmosphere, then the R that I want to pick should have atmospheres in it. So that's my 0.0821. So now I can start filling everything in. My pressure is 15 ATMs. My volume is 1,500 liters, is equal to N. That's my unknown. My R, because I'm dealing in atmospheres, is 0.0821. And then my temperature is 318 K. I need N by myself, or by itself, 0.0821 times 318 on both sides. That cancels, and then this is what goes in my calculator. 15 times 1,500 divided by 3 times 0.0821 with 3 sig figs. So we get 861.8. So by the time I got 3 sig figs, I would say 862. And that's moles of methane. So we're not quite through yet. Because we didn't want moles of methane, we actually had grams of methane, but that's easy to do with the molar mass. So I would find the molar mass of methane, which would be 1 carbon and 4 hydrogens, which comes out to 16.05 grams per 1 mole. So then I'd finish mine out, 862 times 16.05, keeping it at 3 sig figs. So I think you got to do a little rounding on that. 13,800 grams. I'm not sure what you actually got. 862 divided by, oh, not divided by, times 16.05. Yeah, you got like 13,835, but since we can only have 3 sig figs, then that's why it became 13,800. Anybody have any questions on that one? But this little part right here, moving between moles to grams or grams to mole by using the molar mass, is pretty, is something that happens a lot whenever you're dealing with your ideal gas law. Okay, why don't y'all give the next one a try? That one is pretty straightforward. You see that you have the answer 20 with the decimal behind the 0. See if you can get your answer on that one. Mm-hmm. Yeah. Yeah, add 273 to it. Were y'all able to get the 20? There's kind of the setup right there. We are missing our pressure. So if you use a 0.0821, then when you get your answer, then your answer's units will be atmospheres. So because of sig figs, we needed the 20 point with the decimal behind it. Now, when you work the next one, if you'll look at it, you got a couple of different things going on. First of all, your pressure is in kilopascals. So instead of using 0.0821, look at your R's. Which ones would you want to use? Which would you want to use instead?
8.31.
Yeah, 8.31, because if you look at it, it's the one that has the kilopascals with it. So your R that you would use here would be 8.31. When you get down to the third one, you have the fact that you have 12.5 grams of oxygen. And you can't put grams into the formula, so you're going to have to use your molar mass to convert that to moles. So kind of like a reverse of what we did. We have 12.5 grams, and oxygen is diatomic, so that means it has 32 grams per 1 mole. So you're going to need to do that, and then that's going to give you how many moles you have, and then you will be able to plug it into your formula. What about my 350 mils? Can I leave it in milliliters? So I've got it's 350 mils. We move our decimal back 1, 2, 3, so it would become 0.35 liters. You want to keep the same number of sig figs. 350 mils was 2 sig figs, so is 0.35 liters. And then the one after that actually is pretty straightforward. So why don't you give those a try, and then after this answer is 42, this one is 11 in Kelvin. And then by the time you subtract 273, it becomes 262 degrees Celsius. And then the last one is 0.040 moles. So why don't y'all give those three a try?
What was the last one?
0.040 moles. Or at least a couple of them, and then see if y'all need me to work them for you or not before we leave today.